Hello everyone, so we're continuing the topic of diodes. We're going to look at their IB characteristics and we're going to look at their forward and reverse bias conditions. So you saw that PN junction diodes can be built by placing a P-type semiconductor close by an N-type semiconductor. So if you do so, because the P-type semiconductor has a high concentration of holes and N-type semiconductor has a high concentration of electrons, the holes diffuse to the N side and the electrons from the N side diffuse to the P side, and at the close vicinity of the junction, which is here, the electrons and holes combine, and as a result the N side is going to be next to the junction and the N-type semiconductor is going to be positively charged here, and from the P side next to the junction it's going to be negatively charged. As a result, an electric potential or an electric field appears across the depletion region. This is called the depletion region, and this electrical potential or the voltage barrier, which is also called the junction built-in voltage, inhibits the further flow of electrons from the N side to the P side or holes from the P side to the N side. Without applying any voltage across two terminals of the diode or PN junction, this PN junction is going to be in equilibrium and no current flows from P to N or from N to P. However, if you collect a voltage source to two terminals of this junction such that the positive terminal, the voltage at the positive terminal is greater than the node voltage at the negative terminal, as you can see here, or VD is greater than 0, it is called the forward bias condition of diode. And on the other hand, if the voltage at the negative terminal is greater than the positive terminal, or in other words VD is less than 0, then we're going to say that the diode is reverse biased. So in the case of reverse bias condition, the diode does not conduct, or ID is going to be almost equal to 0. For the forward bias condition, the diode is going to conduct, but in order for the diode to fully turn on and conduct, you need to have a voltage source which is greater than this VD node junction voltage, which is going to be 0.6 to 0.7 volts. So if you need to increase the voltage source or the voltage difference between VD, the positive terminal of the diode, and negative terminal of the diode, such that that would be greater than 0.6 to 0.7 volts. At that point, the diode is going to turn on, and this is where the diode turns on. So for the voltage for VD less than 0.7 volts, we're going to say that the diode does not fully conduct. Although it's forward biased, but it's not fully conducting, and next in the piecewise linear model we're going to say that it is off. So let's look at the equation I versus V for the diode equation. So as you can see, it is a nonlinear and exponential equation. Is in here is saturation current is in the range of like pico-nano atto-amps. VT is thermal voltage is equal to 26 millivolts at the room temperature, and is a characteristic of semiconductor. It's going to be between 1 and 2 for silicon. You're going to learn about the derivation of this equation, IV equation, in the future courses. If you are interested in semiconductors, you can learn about these derivations. But for this course, we're going to use the already derived equations. So if for larger current values, when ID, the current flowing through the diode is much greater than Is, or when the diode fully conducts, we're going to use this equation. And this equation, again, it's an exponential equation. We are not going to use this specific one for the case of solving diode circuits, but we're going to use it for solving transistor problems. So for the case of diodes, for solving the diode problems, we're going to use the piecewise linear model of the diode, in which the diode IV equation is approximated by two lines. So we're going to say the diode IV curve consists of two lines, and that is, when the diode is on, VD is going to be equal to VD naught, and the current through the diode has a positive value. When the diode is off, ID is going to be equal to 0, and voltage across the diode, so this is my ID, always label it this way, positive, negative VD, and the current is in this direction. For these current and voltage labels, when the diode is on, VD is going to be equal to VD naught, and ID is greater than 0, and when the diode is off, VD is less than VD naught. So for the case of silicon, as you saw, VD naught, or the built-in junction voltage, is equal to 0.6 to 0.7 volts. So we're going to solve this diode problems using the piecewise linear model. We're going to replace the diodes with their voltage circuit models, depending on whether they're off or on. So if they are on, we're going to replace the diode with the symbol of a voltage source, but that doesn't mean that it's a voltage. The diode supplies voltage. It just means that a voltage equal to VD naught is dropped across two terminals of the diode, and when it is off, the diode becomes an open circuit. No current flows through it, and the voltage across two terminals is equal to VD. So as an example, here you can see I have a diode circuit in here, and if I start solving the diode problem by assuming that it is off, then I'm going to replace the diode with an open circuit symbol, and the voltage across two terminals is equal to VD, and so ID is going to be equal to 0, and if I assume that the diode is on, that means I can replace the diode with its diode model, circuit model, and that is a voltage symbol of a voltage source. But again, it doesn't mean that it generates, supplies power, supplies voltage. It just means that a voltage across equal to VD naught is dropped across two terminals of the diode, and ID is greater than 0. So another way of looking or solving the diode problems is by looking at the node voltage at two terminals of the diode, assuming that you have a silicon diode with VD naught equal to 0.7 volts. When V1 minus V2 is less than 0, then diode is reverse bias and ID is equal to 0. Now if V1 minus V2, or this VD, is between 0 and 0.7, diode is forward bias, but it is not on yet. So I am looking at this piecewise linear model. This is VD and this is ID. So for this range, the diode is reverse bias here. When VD is in this range between 0 and VD naught, the diode is forward bias, but it is not on yet. The diode turns, as a result, ID is equal to 0. When V1 minus V2 is equal to 0.7 at this value, when VD is equal to 0.7, the diode is forward bias and it is on. ID is going to be greater than 0, greater than or equal to 0, and voltage drop across the diode is a fixed value, it's equal to 0.7. From that, I can figure out when the diode turns on or off. For example, in this circuit, if the voltage difference at two terminals is equal to 0.7, the diode is going to turn on. in other words, to turn this diode on, I have to have 0.7 volts from here to here. That means if Vi is equal to 0.7 volts, this voltage source can turn the diode on, and for any voltage value greater than 0.7 volts, 0.7 of it is going to be dropped across the diode, and the rest of it is going to be dropped across the resistor. For example, if you have 3.7 volt from your voltage source, 0.7 of it is going to go across the diode and 3 volt is going to drop across the resistor.